Here we have two LTI systems placed in cascade, where the output of the first is the input to the second. And we're given the transfer function of each of these, h1 and h2. And we're asked a series of questions. The first question asks for the combined transfer function. So h of s, that means y divided by x. So the combined transfer function h of s is y of s divided by x of s. But because we don't know x, we don't know y, that's not helpful. So to find the transfer function, because they're in cascade, you would say the combined transfer function is the product of h1 multiplied by h2. So if these were impulse responses, you would use convolution, but because they're in the frequency domain, in the S domain, we multiply. Okay, so that's how you would answer the first question. But that's not enough, obviously. You need to actually carry out the multiplication. Now, all you really need to do is multiply the numerators and multiply the denominators. You don't need to open that out. So it's enough to leave it in that form. So that's all you need for the 5 marks. You would need to mention that you're multiplying, you need to show what you're multiplying, and you need to give the final product. So that's the transfer function h of s. The question then goes on to ask for the impulse response. So the impulse response h of t is the inverse Laplace transform of h of s. So we need somehow to find the inverse Laplace transform of that if we want to find h of t. So we'll try to find the inverse Laplace transform of that, but there's nothing like that in the Laplace transform table. So we need to split this into terms that we will find in the Laplace transform table. So doing that split requires partial fractions. So we're going to convert this into 2 fractions. And because one of the terms is a quadratic, you have the power 2, then it's not enough just to have an a and a b. We also need this additional term c. So we'll have b multiplied by s plus c. So we have 3 variables in total we need to find, a, b, and c. So unify the denominators and try to write this as an expression. So you've got a multiplied by s squared plus 1 plus bs plus c multiplied by s minus 1 equals 3. Different ways of doing partial fractions. The way I prefer is to just choose values for s that will make this easy to simplify. So I'll choose s as being minus 1, so that becomes 0, and you have 2 times a is 3. So that gives you a value for a. Next, I would choose any 2 other values for s, like 0 and negative 1, for example. So if I choose 0, and you substitute 0 there and a 0 there, that'll give you an equation where b is removed, and you can then find c. So we found c to be minus 3 over 2, so that's our second constant. I then chose s to be equal to minus 1, and this time, because I know a, I can replace that, and because I have found c, I can replace that. Now I have an equation with only one unknown. If you rearrange that, so you multiply those, move the b to the other side, you end up with b being minus 3 over 2. So now you found A, B, and C, A, B, and C. You can write your transfer function as a fraction or a combined fraction. There, so that looks fine, or at least it looks better than it did, but they don't want that. The question is asking for h of t, so we still need to find the inverse Laplace transform. So we need to look these up in the table. So the first thing I'll do is I'll split these into 2, so I have 2 fractions there, and I'll get rid of the 3 over 2. So the constants can be turned into coefficients, and this just becomes s plus 1. And then I can split that into 2. So you've got 1, 2, 3 terms, and the constant term there. So then the Laplace transform table that's provided in your exam paper, you just look each of these up. So this looks like it's right there. So that's e to the at, where a will be equal to 1. So that's your first term. And your second term looks like it's a cosine there. And again, a is equal to 1. So that's a cosine term with a equal to 1. And this looks like it's a sine term, again, with a equal to 1. So now we have our impulse response. We need to remember that the impulse response for a causal system will only be non-zero for t greater than or equals 0. So it's important that we multiply by a unit step. Okay, so make sure you have that unit step there. You'll lose marks if that's not there. Even though that you don't see that on the table, because we're finding an impulse response, it's really important that you have that unit step. Now, part C asks for the step response. So the step response, s of t, is the integral of h of t. And you integrate from minus infinity until t. So it's the integral from minus infinity to t of h of t. But you can't use t here because t is the variable we're using there. So we use some temporary variable, alpha or tau there, or x. So if you're integrating this from minus infinity to t. And it's really easy because you have 3 very easy terms to integrate. That's what you're going to be integrating. Now the important thing is, how do we get rid of the unit step? Remember, a unit step is really just 1. That's all it is. But it's only 1 for t greater than or equal to 0. So what the unit step actually does is it changes the limit of the integration from minus infinity to 0. So this is as a result, of the unit step. And then it becomes a straightforward integration because you're integrating an exponential, a cosine, and a sine. So the exponential is unchanged, the cosine is a sine, and the sine is a minus cosine. Now you just substitute your new limits. So imagine if that was minus infinity, you would not be able to find that. So it's important that you change the limits, and the change in limit comes about because of the unit step. So sine 0 is 0, cosine 1 is 1, and e to the power 0 is 1. So you can now simplify your integration or your result, because you've got -1 and another 1, so you've got -2, and that just disappears. You'll notice that once again we've added a unit step. Why did we do that? That's not just the same unit step reappearing. No, this is a unit step saying that this integration will only be non-zero if t is greater than 0. So it's just our way of saying t greater than or equal to 0. We're just saying it by multiplying by a unit step. So that is my step response. It's the integral of the impulse response. So the final part of this question, it says find the response to an input that looks like that. So we have some input and we're being asked for the response, the output. So how do you find the output in terms of the input? Well, it's straightforward. You just carry out a convolution between the input, this, and the impulse response. The impulse response we've already found. So there you go. Take the impulse response and carry out a convolution with the input. But that doesn't look like fun at all. That's quite a big expression. So to avoid the convolution, what we often do is multiply in the frequency domain. We've got h of s, but again, that's quite a big expression. H of s was that. We're going to have to multiply that by x of s, which is that. So we're going to have to find the Laplace transform of that. And then multiply, and then do an inverse Laplace transform using the table. So again, quite a lot of work. So for 5 marks, I don't think that's reasonable. Is there a better way? Well, if you look at it and realize that this is just a step, and we already know the step response. We just found the step response up here. That's the step response. So if the input is a step, the output should be a step response. If it's multiplied by -5, then the output will be the step response multiplied by -5. But wait, we have a delay. So it's a delayed, scaled step. If we have a delay, how is that going to affect my step response? Well, we just multiply by e to the power -s. So when there's a delay by a samples, you multiply by e to the -as. So if it's delayed by 1 sample, you simply multiply the response by e to the -s. So this is my input. There's a 1 sample delay and there's a -5 scaling factor. So the output, okay, I don't know why I called that x. So what I should have done is say that's the output and this is the input. Right, so my input is x of t, my output is simply, no, actually that was right. So the output is the step response delayed by 1 sample multiplied by -5. So s, that's my step response. So if I get s from up here, all I'm doing is recreating it, but instead of t, I'm writing t -1. So there's a delay by 1 sample. And it's multiplied by -5. And because it's asking for the response in the time domain, I don't need to then use the Laplace transform table to find this in the frequency domain. That's your final answer, and that's 2 lines of work worth 5 marks. So all you need to do is realize that that is actually a delayed step. So that's the answer to that question. I hope you found it helpful. It goes through most of the things you need to know about dealing with a cascaded set of linear time invariant systems where we need to find both the impulse response and the step response. There was a bit of partial fractions going on. I hope you didn't find that too difficult.